what is NASA? What makes NASA unique? Why is NASA not the Air Force? Why is it not NSF? Why is it NASA? There's some things that come to your mind, at least to my mind. What comes to my mind are a strong research and technology competency, a strong flight hardware development competency, and a strong mission operations competency. In fact, it's the synergy of all three of those core competencies that make NASA the unique agency that it is. There is no other place in this country where those three things are together. And it's because that NASA embodies those three core competencies, and always has, actually. You can go all the way back to the Space Act and the formation of NASA, and it calls out these three critical core competencies. It's because NASA embodies all three of those competencies is why NASA is so inspiring to young people, right? If all we do is research and technology, right? So I'm the chief technologist, and I'll tell you this. If all we do is research and technology, and we don't do flight hardware development, we don't do mission operations, then what's the point? We're just NSF, right? We're just off playing in our sandbox, developing little toys, technology toys. I don't want that. On the other hand, if we don't have any research and technology, and we're just building flight hardware and flying it, then we can only take what I would call a rather incremental approach to that flight hardware development, right? So to me, a healthy NASA, a NASA on the cutting edge, is strong in research and technology, in space flight hardware development, and in mission operations. And what the President's FY11 budget request really embodies is kind of a bringing up of the research and technology competency. By the way, not to an equal point. There's still more dollars in flight hardware development and mission operations, as there probably should be. But bringing it up to the point where it's actually visible. Now, how are we going to make these technology investments? And this is a key point. The way we're going to go about that is by identifying the needed capabilities and then investing in multiple competing approaches, multiple competing technologies to achieve that capability. The challenge with this program is that, in my view, we're not actually wise enough today to know exactly what technology is the one that's going to allow us to send humans to Mars or send humans to an asteroid, right? So we don't want to, I for one, don't want to bank my entire human exploration program on some technology that's not yet proven. So instead, we know there's a certain capability that we need, and we need to invest in multiple competing approaches to advance that capability, and then make a down selection a little bit later in time, and take that down selected technology and prove it in a flight relevant environment. And I'll give you some examples of that in just a minute. Now, the other thing that people ask me all the time is, well, we're going to spend 2 years figuring out what technologies or what capabilities we need to go after. Well, thankfully, we don't need to. In my office today, you can come to my office anytime and you can see, I have a stack of reports. And they go from the floor to almost my height. I'm just barely taller than the stack. I'm very proud of that. I'm taller than the stack. It's like the only thing that I'm taller than. And these reports are all, by the way, they're done by blue ribbon panels, presidential panels. They're done by NASA folks. They're done by NRC. They're done by all kinds of groups. And here's a list of some of them. Going all the way back on the left to 1969, the post-Apollo space group, the Space Task Group that was chartered to figure out what are we going to do after the Apollo mission? What kind of technologies do we need to invest in to enable future human exploration? 1969. Jumping forward in time to 1986, Pioneering the Space Frontier, which, by the way, if you haven't read it, is perhaps the most well-done report on this subject of all time. It is by far and away my favorite report. The leader, the chairman of that report was Tom Paine. It's wonderfully presented. And then you can jump forward, we can jump over Sally Ride's report in '87, some internal NASA reports, including the 90-day study that I was, and actually Phil Sumrall were a part of back in '89. Augustine 1 in 1990, his first report, going all the way to the latest Augustine report on the right-hand side. Now, you might not be able to read this slide all the way in the back, but what I've listed here on the rows are some of the technologies that these reports have said we should invest in. closed loop life support, in-space propulsion, heavy lift launch vehicle, entry, descent, and landing, lightweight structures and materials, advanced EVA systems, so on, communications technology, okay? And you see the X's? There's a remarkable consistency from report to report. We know what capabilities we need. We know. It's been documented over and over again. It's right here. What we need is to synthesize this information and use it to develop plans forward. Right? These are the capabilities. What are the technological solutions that provide these capabilities? So we can take these capabilities and we can, if you wanted to do it purely in a competed environment, you could imagine like a call coming out for each one of these capabilities, and different teams could propose back different technological solutions. Or we could take one of these capabilities and we could say, JSC, you guys go lead a team to do this. Langley, you go lead a team to do that. Marshall, you go lead a team to do that. And we'll try 3 different approaches. Right? We could do this either way. And what we're planning to do actually is a combination of both. There'll be both directed assignments and competed. So at a high level, this is where we are, in my view, in the human spaceflight program. In this decade, what we're talking about is involving the commercial sector, both in launch and in other ways. We're talking about robotic precursors, and we're talking about utilizing the International Space Station as the core of our human spaceflight program, flying it out, if you will, through its full life of 2020 and potentially beyond. And we're talking about technology development to enable the systems development for the next human spaceflight system starting perhaps in the 2015 timeframe, so that we can get to a near-Earth asteroid by 2025. So in 2015 or so, we're talking about the design and development of heavy lift systems and in-space capabilities that would allow us to achieve that mission, with the operations for those missions in the first part of the next decade. First in the Earth vicinity, and then eventually to a near-Earth asteroid. If we have a set of goals, like we do, an asteroid mission in 2025, going to Mars, in orbit about Mars in 2035, to the surface after that. From those goals, we can develop mission architectures. From those mission architectures, we can develop flight system concepts. From those flight system concepts, we can develop the technologies required to enable those spacecraft, to enable those missions, to enable those goals. It's a nice requirements flow down kind of approach. And this is the approach that ESMD, the Exploration Systems Mission Directorate, is using through the HEF team. This is not the only way we're doing technology development, but it is a big part of the plan, right? And it's organized in a very, what you would call a systems engineering way. This is what the team has come up with to date. One, there are a lot of missions. There are actually a lot of things. In terms of sheer number, there are a large number of technology development items that are going to go into space. There are a large number of launches as a result, and there are a large number of mission operations opportunities as a result. There are also a large number of hardware development opportunities to get these technologies ready and to develop them and fly them, right? Whether we're talking about the Human Research Program or the Heavy Lift Program, which has both a launch and an in-space component, there are development opportunities. This is not a technology program that is all about playing in our academic labs. This is a technology program that spans concepts, ground and laboratory testing, flight testing, and testing in space. So I'm the NASA Chief Technologist, and one of my responsibilities is to plan out all of the NASA technology programs, those within the mission directorates, and the new technology program called the Space Technology Program. That's a brilliant name. I didn't come up with it. Within my office, the Office of the Chief Technologist. And here is a view of all of those technology programs together. What I have at the top is the Space Technology Program. And what I have on the bottom here is just Exploration Systems Mission Directorate as one example of a mission directorate. You should realize that there's technology investments being made in science, certainly in Aero, and in SOMD as well. But for ESMD, these are the programs that they're formulating. And across the bottom here, I have technology readiness level, right? So TRL of 1, your concept studies, your system studies are all the way over here on the left. And flight missions, operational missions, are over here on the right, right? Our operational portfolio of missions. Within space technology, there will be low TRL programs. We're going to look broad and wide for the best ideas, wherever those ideas may be. We're going to look internal to NASA. We're going to look at academia. We're going to look internationally. We're going to look at industry. You may remember the NASA Institute for Advanced Concepts. Anybody remember that? Okay, it was around for a large number of years. Its budget was cut a few years ago, partially to make room for Constellation. It was, by the way, it wasn't in my view, it wasn't purposely cut. It was just out with the sweep. There was a sweeping done of all the technology programs at NASA at that time, and the NIAC was eliminated along with a number of other things. We're going to reinstate the NIAC. We're going to reinstate the NASA Institute for Advanced Concepts. That's one example of the kind of concept development program that we're going to have. It's not the only one, but it's just one example. Over here in the middle of the page, we have what I call your mid-TRL kind of things, your TRL 3, 4, 5 kind of programs. This is where all your ground-based testing, your laboratory programs are going to be. I've done a lot of concept studies in my life, and I'll tell you, on paper, they all look beautiful. And every time I get involved in a concept study, there's only like this one little piece of physics, right, that's holding it back. If only I could prove this little piece of physics work, then the whole system would look great, just like I've shown in this system study. Well, we're going to go after those little pieces of physics in these programs, both within the mission directorates and within my office, the Office of the Chief Technologist. And then we're going to take some of those things, some of those pieces of physics that we prove in the lab, prove that they are feasible, and we're going to take them to flight. And we're going to prove those technologies in a space environment, right? And once again, the renewed emphasis on technology, by the way, which has been suggested over and over again by a number of external groups, is really, in my view, a rebalancing of NASA's 3 fundamental core competencies that have really always been in existence. Now, what this will do for NASA, in my view, is it will provide a much more likely set and a much more exciting set of potential futures for our science and exploration missions. Okay? It'll definitely improve, in my view, the space program. And the reason I think that we are is because we don't know exactly what that heavy lift vehicle is. How big should it be, for example? Is it 80 metric tons? Is it 150 metric tons? Is it 200 metric tons? See, now I'm getting Phil really excited. You like 200 metric tons, yeah? Yeah. And so obviously if we have a 200 metric ton vehicle, right, just as an example, then maybe we don't need as efficient of an in-space engine. Right? 'Cause we can just lift up a lot of stuff. Maybe we don't need propellant depots. But if we're down around 80 metric tons, then all of a sudden the case for in-space propulsion and propellant depots, since 80% of the mass is propellant, starts to make sense. So I think you're right. But I think this is a great example of why we need a parallel investment strategy in all 3 of these areas.